Hello, everyone. Thank you for joining us for our second seminar. This is the second seminar in our three-part series. Our first seminar was 2 weeks ago on October 17th. If you were unable to join us for that seminar, you can still watch it live on YouTube. Today, we're going to have two speakers from Princeton again, Beryl and Ciaran. And our third and final seminar will be in 2 weeks on November 14th at the same time, 11 a.m., 1 p.m. Pacific Standard Time, or 2 p.m., 4 p.m. Eastern Time. So this event was created and organized by the American Chemical Society Student Chapter at Cal State San Marcos. Here are some pictures of our 2020-2021 officers. So here is Alma, she's our president. This is me, Emily, I'm the vice president. And our treasurer, Amanda, our secretary, Kaylee, our historian, Jennifer, and our public relations officer, Alondra. We actually found out this week that our club won an outstanding award for the work that we did last year. And this event is also in collaboration with the Princeton University Chemical Society, and one of their officers is going to talk a little bit more about this slide.
Thank you, Emily. My name is Vin Tan, and I'm the events coordinator for the Princeton University Chemical Society. And on behalf of everyone at PUCS, I'd like to thank the student ACS chapter at Cal State San Marcos for this wonderful collaboration. And we also thank Beryl and Ciaran for speaking today. We sincerely hope you enjoyed today's seminar. Back to you, Emily.
Thank you, Vin. So let me just go over quickly what our agenda is for the day. Right now we're doing introductions. Then after this, Beryl is going to be presenting and followed by 10 minutes for questions. And then Ciaran's going to present followed again by 10 minutes for questions. And as a special treat for those joining us in the Zoom audience, there's going to be a 20-minute Q&A discussion at the end of the event. So how to ask questions. If you're in the Zoom audience, there are two ways for you to ask questions. You can either raise your virtual hand by clicking on the Participants tab, or you can type your question in the Zoom chat. For those watching on YouTube, you can email your question to steminar.questions@gmail.com. This email will be listed in the description box below the stream. And with that, you can connect with our club and see everything that we're doing if you follow us on Instagram or Twitter at CSUSM-ACS, or you can email us at CSUSM-ACS.club@gmail.com. With that, I would like to hand things over to James, who's going to be our moderator for the event.
All right, well, thank you very much, Emily, for organizing this, along with the ACS at CSUSM for making this happen. And also thanks to Princeton ACS for joining us today. I was on the ACS committee when I was an undergrad, so it's really exciting to see how far it's come to this point. So I am, just a bit about myself, currently a third-year grad student here at Princeton University. I work with our speakers today, Ciaran and Beryl. And like many of you in the audience, I did my undergrad at CSUSM. So I worked with Dr. Ife for about 2 years doing undergrad research in gold catalysis and asymmetric organocatalysis. And I'll be moderating the questions today. So as Emily mentioned, feel free to ask your questions at the end of the talk. But today is not about me. It's more so about our two incredible speakers today, Beryl Li and Dr. Ciaran Seath, who I have had the distinct pleasure of being colleagues with. And so our first speaker today is Beryl Li. So just a little bit about her. Beryl is a fourth-year graduate student in the Macmillan Lab, 1 year my senior. Beryl is a very worldly and well-traveled individual. She spent her time growing up between two cities, Beijing and China and Vancouver, Canada. But eventually she sort of decided to become a Californian. Unfortunately, she chose the wrong half of California, the northern half. So it doesn't really count, but that's okay. We all make mistakes. And while she was in Northern California, she attended UC Berkeley to pursue her undergraduate degree in the chemical sciences, which makes her rather unique here in our department, as I think only around 60% of the grad students here are Berkeley alumni. So really stands out there. But while at Cal, she worked at, she did undergraduate research in the lab of Professor Richmond Sarpong on the total synthesis of C19 diterpenoid alkaloids. which means that she had plenty of time to go out and really get and enjoy the full college experience. Case in point, she had an internship at Genentech in their process chemistry department, where she worked on synthesizing tetrasubstituted all-carbon olefins, which we abbreviate as tacos, of course. But after Genentech, Beryl ventured out to the East Coast to join the Macmillan Lab here at Princeton. And as an aside, Beryl is an excellent chef. Perhaps that came with all of her experience making tacos at Genentech. And the lab is very fortunate that she's so generous with her cooking, and she brings treats and pastries to us to keep us well fed, which is something that Dave certainly does not do. So it's very nice of her to do that. And it's been an absolute joy to work with her and to occasionally rotovap her fractions for her late at night. So with that, please join me in welcoming Beryl to the virtual stage. Beryl, you may begin your presentation.
Thank you, James, for that surprisingly kind introduction. Can everyone hear and see me okay? So thumbs up? Okay, sounds good. Well, hi everyone, my name is Beryl. As James mentioned, today I'm quite excited to share with you some research I've done here at the Macmillan Group, but also how did I get to where I am today. So a little bit about me. As James mentioned, I grew up really bouncing around quite a bit. I was born in Beijing, China, and then moved because my mom's work to Vancouver, Canada when I was 6 or 7. So I actually then went back to China and back to Vancouver and went back and forth a few times. So shown here are actually all the schools I attended before the 9th grade. So for high school, I finally moved down to California from Vancouver and went to high school in Santa Rosa, which unfortunately probably most recently became known nationally because of the 2020 glass fire. So it's quite torched up a bit right there. But before the fires, Santa Rosa is probably best known to the world as home to the cartoonist Charles Schulz and the Peanuts comic strip series. So in high school, I wasn't particularly interested in chemistry. All I knew back then is that I'm reasonably good at math, and physical sciences, your collection of chemistry, biology, physics, geography, all seemed pretty interesting. So it really was a sort of coincidence that I ended up applying to Berkeley's College of Chemistry. But it turns out that that was sort of the most prestigious program I got into. And my high school self just picked college based on that. So I landed in Berkeley College of Chemistry really by chance without really understanding what I'm getting myself into. Now, my first foray into actual chemical research was by joining Richmond's lab the summer before my junior year. So by this point, most of my classmates have already started working in labs and getting real research experience, because that's something Berkeley really values. And I felt like I was really falling behind by not starting research in my first 2 years of college. So the way I joined Richmond's lab was actually slightly unconventional. Instead of doing the sort of more well thought out thing of applying to an undergraduate research program and going about the formal route, I essentially looked up Richmond's group meeting times on his website and barged in and just sat in the group meeting. And then after group meeting, I think it was Monday nights, 6 to 9, right? I just, went up to Richmond, cornered him, and gave him my resume, which, really doesn't contain much at the point. And what he told me, which in hindsight is really, I think, him letting me down easy, is he said he'll take me as long as I can find myself a mentor in his group. And I'm pretty sure he was banking on the fact that no one would take me in, right? And that's just sort of letting me off easy. So after the chat with Richmond, I looked at all his people on the website and I found Kevin, who from his bio on the website also grew up in Vancouver. So I was like, okay, he looks nice, I'll go talk to him. So I emailed Kevin, asked to meet. And during our meeting, there really wasn't any sorts of discussion about whether I would join the lab. Kevin just started the conversation with, okay, so how many hours do you want to work? And it turns out, as he told me, probably 4 months after I started, he actually saw me talk to Richmond, and he had assumed that Richmond already accepted me, and he didn't have a choice, and he had to mentor me. So through this sort of delightful misunderstanding, I was able to, get into a lab and do research. And it's only after joining the lab that I actually understand a little bit more of what the Sarpong lab does. So the Sarpong lab does a lot of what's called total synthesis, which essentially is just the complete synthesis of a complex molecule, often natural products, from these sorts of simple and commercially available precursors. It's quite a labor-intensive subfield of organic chemistry, where sometimes, a single graduate student or postdoc can spend, years working on a target. And if you can, complete the synthesis of something, that's a fairly respectable amount of work for your PhD. The pursuits are rather academic in the sense that the sort of manpower to utility ratio could be rather high, but because the targets themselves are so challenging, this provides very good training in, sort of setting up reactions and thinking about chemistry for the students. And as an added benefit, again, because the targets are often so challenging, they inspire rather creative methods and strategies in putting these molecules together. So a little bit about the project I was fortunate to join. So shown here, as James alluded to earlier, is the scheme of this paper talking about a unified strategy towards synthesizing these diterpenoid alkaloid molecules. So a little bit about their names. These molecules come from these isoprene units, which contains 5 carbons each. These are one of the sort of more common building blocks in biosynthesis to sort of build a large variety of natural products. So for example, you have this menthol here shown on the right. And if you trace the carbon skeleton, you can actually see menthol comes from 2 of these isoprene units. So menthol is known as a monoterpene because it has 10 carbons in its skeleton. Now, if you put 4 of these isoprene units together, you get something called a diterpene, and they can sort of come together in a very large variety of ways. But they're generally called diterpenes because they have 20 carbons in their scaffold. Now, if you modify these scaffolds, like if you oxidize them and attach additional functional groups, we then call these things diterpenoids. And finally, if the diterpenoid scaffold itself contains a nitrogen, often basic, we then classify them as diterpenoid alkaloids, which are all of these molecules here shown on the screen. So while this sort of overarching project is really quite impressive in nature, my contribution is very small. Specifically, all I did in my undergraduate years is make the blue portion of this middle intermediate. So shown here on the scheme is literally all the reactions I've ever run in that lab, shown here on a tiny square, right? But I did run these many, many times on very large scales. So with photosynthesis, right, there's going to be a lot of sort of work done, sort of 10, 20 steps into the sequence. But that requires a large amount of starting materials to support the sort of late stage studies. And as an undergraduate, my sort of task is to sort of continuously bring through these starting materials on very, very large scale, right? So we have anywhere from 10 to 80 grams of material. So at this point, I had, I think, spent about a year and a half working in Richmond's lab, and I really got my first taste of research, right? I sort of became more accustomed to setting up reactions and really translating what I learned from textbooks from my classes into sort of real life flasks and actual products and material. However, at this point, I would say that I really didn't have much of my own sort of ideas. A lot of it is Kevin, my mentor, telling me what to do, and I go execute it. So while it was a lot of very good practice, I looked forward to something that's sort of slightly more intellectually independent. The other thing that's worth noting, actually, is by the time of joining Richmond's lab is about when my GPA really started to drop, because at this point I would be spending my mornings going to classes, and come lunchtime I would essentially come into lab, park myself there, and work almost past midnight every day, just because phthalosynthesis in of itself is such a labor-intensive field. So basically, the sort of more hours you spend at the bench, the more productive you will be, right? So I really shifted the focus of my life away from studying and really into doing research. So after about a year and a half in Richmond's lab, I was very fortunate to have them recommend me for an internship at Genentech, which is a local pharmaceutical company in the Bay Area. And there I was able to work with a variety of very talented, very capable colleagues and managers. And we belonged in what's called the process chemistry department, which their job, the actual employees, not the interns, their job is to design and execute syntheses of any sort of promising drug candidates to support preclinical and clinical trials. So these would often be prepared anywhere from the decagram to the kilogram scale. Now, if you look at the sort of drug development pipeline, right, process chemistry really sort of falls into the middle two arrows, the preclinical and the clinical trials phase. I really liked my time there. One of the reasons is that process chemistry really sort of straddles between two different parts of the drug development pipeline, right? So on the left here, they really talk a lot to the medicinal chemistry side, where their job is to identify and synthesize many drug candidates at very small milligram scale for any sort of biological assays. So on the other hand, while the materials are being prepared on a kilogram scale, process chemistry also has to talk to chemical engineering and formulation to really transform, your sort of product in the flask into a pill someone can take, right? So I was fortunate to be exposed to sort of a large variety of tasks and responsibilities by virtue of being in that department. Now, where the interns come in is actually exclusively for the publications. So because process chemistry often has to prepare a lot of materials, from fairly inexpensive sort of starting materials, there's a lot of work put in to really designing highly efficient and robust or green reactions. And these reactions, in addition to supporting the drug development pipeline, also has academic value. So the interns would essentially take these reactions developed and sort of spin them and complete them into actual publications for the world to see. So specifically, what I had the fortune of working on started off from this GDC 0810 molecule. So this particular molecule is a selective estrogen receptor degrader, which means it binds to estrogen receptors and causes it to be degraded and thus downregulated. So you can imagine that this would have implications and it would have value in, say, breast cancer or other sorts of diseases, right? The actual fate of this molecule is not great. I don't think it eventually made it to sort of the end stage development. However, in addition to this particular molecule, the blue bond highlighted in the middle, these tetrasubstituted double bonds, are actually quite a desirable motif applicable in other useful molecules, right? So shown here are just 3 of the drugs out there that feature these bonds, right? So although the actual molecule GDC 0810 didn't go through, the sort of knowledge and methodology developed in constructing these bonds are still of value. So my job really was to expand this and bring it to publication. I spent around a year and a half there, first as an intern, then as a part-time employee. I was able to sort of, with a lot of help, of course, bring through these 2 methods for constructing these really congested double bonds. Now, in the process, right, I was able to really follow a methodology project, right, through the sort of optimization stage, run out my substrate scope, prepare the manuscript. And it's also around this point where I formed my preference of working on methodology development over making synthesis. For me personally, I find it more rewarding to sort of develop methods that can be applied to many other molecules rather than focusing on a single target. So in addition to the sort of scientific growth I had at Genentech, the other really valuable thing I learned is really just by talking to and observing a lot of the colleagues and my managers there at the company, and they really formed very good role models for me, not just in terms of science, but just in terms of careers and just life in general. Right. For example, Haiming is Chinese, and he, I think, immigrated to the U.S. for his graduate school, right? And then, settled down in the Bay Area. Natke, I think, did his college in Canada, and he too, came over to the U.S. Diane just had her first baby, I think, a year and a half before I joined. So I was able to, talk to her and see, how does that work when you're at the bench working, right? So I think around this time, by sort of looking at them and talking to them, I really sort of cemented my motivation to go to graduate school, right? Because at this point, I've found out that really, I like to work with my hands and run experiments. I enjoy collaborating and talking to people about science. And also, more importantly, if I want to ever come back to Genentech or go to a pharma company like it, I'll need a PhD, right? So that really sort of motivated me to eventually apply to graduate school. And this brings us to my time in the Macmillan Group. So here is where I'm gonna switch gears from talking about myself for a little bit and give you one story of one of the projects I've worked on in the Macmillan Group here, namely the photoredox catalyzed tyrosine amination for site-selective protein conjugation. So shown here, right on the screen, is a MBOC proline. And as organic chemists, we're really in the business of making and breaking bonds, right? To do that, you need energy. The sort of most obvious or intuitive way to deliver energy is by delivering heat, right? You heat it up and something happens to the molecule. However, right, if our molecule of interest is swimming in a sea of other molecules, right, simply heating up the reaction vessel would result in universal activation, right? There will be a lot of side reactions, and we can't really selectively deliver our energy to where we want it to go. Now, an alternative or complementary approach to heating your reaction vessel is to use light. With the help of blue light and this iridium photocatalyst, we can selectively energize our substrate, this MBOC proline, and decarboxylate it to furnish this alpha amino radical here. Now, this radical can then go on and engage in coupling reactions with other species in the flask and result in value-added product. And in the Macmillan Group, we've been able to adopt this strategy repeatedly and selectively activate all of these native functional groups, engage in coupling and, create these value-added products. Now, while this has been, obviously a very successful approach in organic chemistry, I would actually argue that photoredox catalysis could also be very powerful in complex biological environments, where instead of being worried about side reactions with small molecules in your system, you're now in a sea of larger and arguably more fragile, more complex biomolecules, right? So the ability of photoredox catalysis to selectively activate a substrate makes it very attractive to be applied in these sorts of biological and bioconjugation reactions. So that's where my project comes in. Specifically, I worked on a site-selective tyrosine bioconjugation using this sorts of photoredox platform, and we're able to arrive at both tyrosine-specific as well as site-selective conjugation reactions. So a brief overview of bioconjugation. Bioconjugation, despite the mouthful of a large word, really just means the attachment of a variety of probes or small molecules to a biomolecule, right? Very often a protein. In my mind, it's sort of, it really operates at the interface of chemistry and biology because you're using a chemical tool to probe any sorts of downstream biological questions. Now, when people think about bioconjugation, usually the first things that come to mind are taking advantage of these nucleophilic residues, such as lysine, cysteine, or serine, shown here. These are very efficient and very robust reactions, which is why people like them so much. However, at the same time, regional selectivity can often be very challenging. So for example, on this imaginary protein here, if you have 5 lysines, right, that are all solvent exposed and accessible for reactivity, it'll be quite challenging to selectively only react with 3 of them while leaving the other 2 alone, right? So as a response, scientists in the community over the years have began investigating in other sort of modes of reactivities that are gated by other factors other than nucleophilicity. This gives you the potential for more homogeneous products because now you're no longer at the mercy of these sorts of solvent-exposed residues, right? So people have looked at, say, tryptophan, the C-terminus, methionine, and tyrosine. A few of them are shown here on the right. Now, specifically, I'd like to draw your attention to the C-terminus, where in our own group in 2018, we're actually able to selectively decarboxylate the C-terminus and produce this alpha amino radical, which then goes on and does a Michael addition to form essentially monomodified products. After publishing the C-terminus methodology, we began looking at other residues that could be similarly amenable to these sorts of reactivities. And tyrosine really looked quite attractive. So for one thing, tyrosine residues have very good open shell reactivities, as shown here, right? If you form a radical, it really is quite stabilized as it resonates around the ring. Furthermore, tyrosine residues tend to be amphiphilic. So that means they could be both hydrophilic, right, judging from the hydroxy at the end, or hydrophobic, judging from the phenyl ring in the middle. So that means they can exist in a large variety of environments where some of them could be buried and other ones could be exposed. And this sorts of variety of steric environments means that certain ones would be more reactive than other tyrosines. Furthermore, depending on their environment, right, the tyrosines themselves can either be electron poor or electron rich, which would influence their somophilicity. So you've probably learned about HOMOs and LUMOs in class, right? That's the highest unoccupied and lowest occupied molecular orbitals. So SOMO just means singly occupied molecular orbitals. This is just a fancy way of saying that tyrosines could have variable reactivities with other radical species in solution. So considering all of this, right, we ask ourselves, can we actually take advantage of tyrosine's different microenvironments and really develop a method that's not only tyrosine specific, but also potentially single site selective, right? Can we hit one tyrosine over all the other ones that might be in the same protein? So we're not the first ones to work with tyrosine conjugation. A few other examples are shown here. So Nakamura has shown that you can activate tyrosines using blue light and a Rubipi photocatalyst. There are also electrochemical as well as enzymatic methods to activate these residues. Now, coming back to our own reaction, we envisioned that we would take a endogenous tyrosine that exists in a native peptide or protein and some sort of radical precursor, the scaffold of which is shown here. Now, the radical precursor, this phenoxazine phenothiazine, could be oxidized to form this persistent in-centered radical. And of course, due to the sort of uniqueness of the scaffold, this in-centered radical is more delocalized than, say, the diarylamine counterpart. This means because the radical is more delocalized, it tends to be more stable. So this radical species can actually be slightly longer lived in solution, waiting to react with our tyrosine residue. And of course, we activate and form this radical with our favorite method, photoredox activation. And this sort of radical intermediate would then engage with the tyrosine and form this sorts of C-N aminated bond. So I had the good fortune of working with Dr. Stephen Bloom and Dr. Daniel Kim, two very good postdocs who are now both off to professorships in their different universities. And the overall project is also in collaboration with Bristol Myers Squibb, a local pharmaceutical company as well. So after some initial optimizations, right, we're able to take this bivalirudin, which is a 20-mer sort of commercially available peptide with the single tyrosine, and with lumiflavin, as well as this phenoxazine dialdehyde here, we're able to demonstrate conjugation up to 95% yield. And this was very exciting because the reactivity we hoped for is there. A few words about the phenoxazine itself. So this phenoxazine dialdehyde is actually our sort of invention. We're able to synthesize it from only 3 steps from commercially available materials. So the preparation is quite simple. Furthermore, the dialdehyde groups on each side of the phenoxazine are actually electron withdrawing, such that it would render this nitrogen-centered radical to be more electrophilic, so more electron poor, compared to, say, the phenoxazine, the parent phenoxazine or the parent phenothiazine. Now, on the other hand, as you remember from earlier, tyrosines themselves are somophilic, right? And tyrosines are actually quite electron-rich in general, right? So the electron-rich tyrosine and the electron-poor phenoxazine can then engage in a polarity-matched reaction to furnish our desired product. And furthermore, depending on the tyrosine microenvironment, right, we hypothesized that the reactivity of it would also modulate depending on like where it sits, which would aid us in developing these sorts of site-selective reactions. Furthermore, the adduct themselves, this phenoxazine phenol adduct, is quite conjugated. And we actually found that the product itself is fluorescent. It emits around 520 nanometers. So really, by using this method, in one chemical step, we're able to take these native proteins and make them into fluorescent aminated products, which, as you can imagine, could be used for a variety of applications, such as microscopy and whatnot. The other sort of really important design element that concerns the dialdehydes is that this really makes our phenoxazine reagent a bifunctional linchpin, where on one side, right, the nitrogen can engage in site-selective reactivity with a native protein, and on the other side, the dialdehydes can engage in what are called bioorthogonal reactivities and allow us to append a variety of useful molecules onto this native protein. So bioorthogonal chemistry just refers to reactions that can occur in a living system without interfering with the sort of native biological processes. You'd be quite hard-pressed to find aldehydes hanging around in the protein. So by putting these aldehyde handles in, this hydrazide condensation actually doesn't interfere with any of the sort of nucleophilic reactivity the protein naturally has. So after our initial success with bivalirudin, we sought to test our method on other substrates that contain sort of proper secondary structure. So we looked at the ZVAR affibody, which is just a sort of truncated antibody. So it's still quite small, only 8.1 kilodaltons, and it only still has one tyrosine. But we're pleased to find that the reaction still worked, even when your substrate is folded into a slightly more rigid structure. Now, what's really exciting was when we tried our reaction on human lysozyme, which is slightly bigger, but now this time has 6 different tyrosines. And we're very happy to find that in this case, we only get a single product reacting on tyrosine 45. So this warrants a closer look. Shown here is the crystal structure of human lysozyme with the tyrosine highlighted in orange. And you can see that not all of them are really poised for reactivity. For example, tyrosine 54 is buried and just simply too sterically inaccessible for any reaction to happen. On the other hand, tyrosine 20, Y20 here is neighboring a lysine residue. So the lysine being positively charged would withdraw electron density away from that tyrosine through what's called a cation pi interaction. That would cause that particular tyrosine to be more electron poor than usual, which means it's no longer poised for reaction with the similarly electron poor phenoxazine. On the other hand, right, Y45, the one that did react, is both surface exposed, but also hydrogen bond donating to perhaps a nearby water molecule, because this is in a largely aqueous solvent. So both sterically and electronically, Y45 would be the most reactive, and that's what we see. So after the really good results with lysozyme, we then tried our reaction on a variety of other proteins with multiple tyrosines. And you can see that in cases such as ribonuclease A and myoglobin, the middle here, we get a single product. And in other cases, we get anywhere from 6:1 to 30:1 selectivity, which sort of supports our hypothesis of the tyrosine microenvironment modulating its reactivity. Now, what's really impressive to us is that this serotransferrin protein, which is a whopping 77 kilodalton with 26 tyrosines, actually has reactivity only on Y136, which was very encouraging. So as far as the mechanism of this reaction goes, we envision having a lumoflavin catalyst. This will get excited by visible light irradiation to form the triplet excited state, which then can oxidize our phenoxazine reagent to furnish this lumoflavin semiquinone, as well as this in-centered phenoxazine radical. The radical itself can go on and engage in bond formation with our endogenous tyrosine, and that would then engage in another proton transfer, electron transfer with the semiquinone to form the fully reduced lumoflavin, which is this H2FL species. And on one hand, we have our aminated product, and on the other hand, to close the cycle, we turn over the catalyst by reoxidizing it with sort of trace oxygen around the reaction. So if you take a closer look at this, you'll notice that this is actually not the only possible mechanism it can go through. Specifically, if you look at the oxidation potential of excited lumoflavin, it's actually quite high. It's all the way up to 2.26. And if you compare that to the oxidation potential of both phenoxazine and tyrosine, you'll notice that it's higher than both of that, right? Which means lumoflavin, oxidized and excited lumoflavin, can oxidize both our reagent as we want it to, as well as the tyrosine that's in the reaction. So why do we propose this and not the other way around, right? To really get to the bottom of this, we collaborated with Dan Oblinski here at Princeton from the SCOLS group, and actually looked at our reaction using what's called transient absorption spectroscopy. So all this does is it shoots a beam of laser to a reaction mixture and excites the species in it, and it shoots a second laser to sort of look at that excitation, and how it decays. So shown here really is the sort of fingerprint of lumiflavin after it's excited, and how it decays back to the ground state. Now, if we mix in human insulin with our lumiflavin, shown on this orange trace, which is really just a proxy for tyrosine molecules, we see that the decay characteristic of lumiflavin stays more or less the same. And this shows that tyrosine, at least in the form of insulin, doesn't quench our lumiflavin catalyst. On the other hand, if we add in phenoxazine dialdehyde, which is our reagent, you see a very significant deviation from lumiflavin by itself. And this gave us sort of preliminary confidence to propose the mechanism that we did, because it seems that our dialdehyde species is more capable of quenching and engaging in lumiflavin in reactivity relative to insulin or tyrosine. And finally, to wrap up this project, we wanted to demonstrate its sort of real-world applicability. So what we did is we took this lysozyme conjugate, which, remember, again, only is modified on a single tyrosine. And we took that and we mixed it with a variety of commercially available oximes or hydrozides. So shown here is a biotin, a fluorophore, as well as these alkyne and azide click handles. And just at an hour, we're able to then furnish these diversified products for sort of further downstream use. And with that, I conclude the sort of scientific part of my talk, and of course, thank the group, thank Dave, thank all of everyone who worked on this project, as well as our facilities here and all of these institutions for funding. Now, I would like to actually end by reflecting on sort of my journey, so to speak, up to this point, right? In terms of research interest, I went from thinking that, STEM is cool, to, I want to make molecules. And then at Genentech, I decided I prefer to do methodology. And in graduate school, I actually took that a step further and pivoted away from organic chemistry and started doing my sort of research in chemical biology and all of these areas. So I think the sort of takeaway here is that it's okay to not really know what your end-all be-all interest is for the rest of your graduate or scientific career, because your interest very well may evolve with time. If you ask me, not even in high school, if you ask me at the end of college if I ever think I'm working with biology, I would tell you, no, I'm definitely not going to do that. But here I am, right? So your interests may evolve, so don't worry too much about it. And as far as sort of scientific growth, I would say that my sort of transition had been moving more and more away from executing other people's ideas to now really training and executing my own ideas, which of course, facing all of the challenges that may associate with that as well, right? Because if you're the one to design an experiment, to probe a hypothesis, whether it works or not, that's on you, right? So I'm definitely still like on my way to really fully, becoming accustomed to that as I progress in my graduate career. And finally, I would like to say that here's my email on the screen. If you have any questions about science or graduate school or anything, feel free to email me. I'm happy to chat about it. And I think that's my last slide. With that, I'll conclude my talk, and I'd be happy to take any questions.
Thank you, Beryl. Let's all give Beryl a round of applause. Great. I of course always love that presentation. I think the rotating protein slide I think will be my all-time favorite slide in any presentation. So with that, I'm sure you all have a lot of questions to ask Beryl. So go ahead and go for it. You can again raise your hand, in which I'll call on you. or just enter a question in the chat. We'll also be having questions from YouTube come in as well. So go for it. Okay, so looks like we have a question from YouTube. So the anonymous individual asked, did you learn all of these lab techniques at Princeton, or did you have to know, how to do these things before you joined the lab?
Yeah, I think that's actually a really good question in terms of like how much imposter syndrome should you really feel before starting graduate school. I would say that the sort of bare minimum, right, is you need to be able to perform all the tasks that your undergraduate organic labs ask you to perform, right? You should be able to spot a TLC, you should be able to run a column, look at an MR, and like sort of know your way around it. However, a lot of the sort of working with proteins and running bioconjugation reactions, really figuring out how to work with things that are not molecules or not organic molecules. All of that I really picked up after I started this project, not just after I started graduate school, right? So a lot of times, much of these techniques you really have to learn on the fly, which I actually think is one of the things that makes graduate school so cool, right? Because you're under a lot of pressure to perform and deliver results. So the sort of picking things up and the learning curve really sort of gets quite steep, and that's part of the fun, I would say.
Great. So any more questions, feel free. It looks like Madison Wagner has a question. So Madison, you can type your question or go ahead and ask it over the video chat.
Yeah, so you said that you use light to activate certain molecules, especially when you have like a whole bunch of molecules in a solution. How do you know which frequency of light or what kind of light to apply to activate just that certain molecule?
Yeah, so that actually depends a lot on the catalyst itself, right? So iridium catalysts, if you look at it in a vial, is yellow, which means it absorbs blue light quite well. So that's how we sort of know that you want to shine blue light on it as opposed to shining, say, red light. If you want to use a red light catalyst, the sort of structure of that would then have to deviate from a analogous blue light catalyst. As far as which molecules you'll end up activating, right? Certain functional groups have a tendency of absorbing light and becoming sort of messed up with it. If you shine UV light, for example, most sort of white molecules or white compounds, which is a lot of them, would end up absorbing and becoming activated. But there really isn't a very good sort of blanket intuition that like, oh, this will get activated, this will not. A lot of it really comes down to running the actual reaction and seeing what happens.
Thank you.
Great. Any more? So another YouTube question. So biomolecules are really large. Do you ever get multiple sites of bioconjugation on the same enzyme/protein?
Yeah, definitely. So shown there on the slides, right, are the 8 or 9 proteins that worked very well, and we will talk about those. There are another 20, 50 proteins we tried that didn't work so well. So BSA, for example, bovine serum albumin, is a very sort of common protein that people tend to have around. And that guy has, I think, 21 tyrosines, and we hit a whopping 16 of them using this method. So yes, definitely. It depends on the substrate.
Right. Thanks, Beryl. So Amanda asked, how many grad schools did you apply to, and how many did you end up choosing? Or how many did you end up choosing, and why Princeton?
Yeah, so my selection of Princeton is actually motivated by very unscientific reasons. So I think I applied somewhere between 8 and 10 schools, I think. And then I, visited all the ones that I got in, and eventually really what drove me to Princeton and specifically to Dave's group is actually the money that we have to run these reactions. So research is quite expensive, even though as a graduate student, my stipend would have been sort of uniform no matter where I go. The fact that I am an international student means I'm ineligible for any sorts of NIH or NSF funding. I'm also ineligible for the Canadian funding because I did my undergraduate in the United States. So I don't get either side. This means if I were to go to a less well-funded school, my selection in the groups would actually have to depend on whether the PIs would be able to afford me. However, Princeton, as you know, is relatively, deep-pocketed. So I know that if I choose Princeton, then I would essentially have free reign in really deciding which group I want to work for without having to worry about funding issues and whether all of that would work out.
Definitely an honest and really great answer. You want to be well-funded in graduate school. So it looks like Roberto has a question. So Roberto, go ahead and ask your question over video or through chat.
Hey, Beryl, I want to say thank you for the presentation. It was amazing, and for all of your really honest and raw responses to the questions that you've been answering. But I'm really interested in the fact that you're in this metallo-organic lab, I guess, and you're running these tyrosine reactions. But my question is, are these, since they're proteins, are you doing this all in aqueous solution? And if so, what kind of solvent system are you using for these these tyrosine reactions that you're running?
Yeah, that's a really good question. Let me actually pull up my conditions slide since it'll be easier to talk over that. So you're right that these reactions would have to run in mostly aqueous system. So they're actually run in this potassium phosphate buffer at pH 7, which is physiological pH. This is the sort of buffer that keeps the protein happy, right? But you also notice that my reaction system contains 5% DMF, which is an organic solvent, and this is actually here to solubilize the phenoxazine small molecule. So what I do is in a sort of say 200 microliter of water containing my lumiflavin and my protein, I would then add in 5 to 10 microliters of DMF stock solution, which contains the phenoxazine. So 5% is sort of the standard that the community will accept. So 5% of organic solvent in your aqueous buffer doesn't really mess with the proteins, but that's sort of where that system comes down to.
Thank you.
All right, great. Thank you all for your questions. Thank you, Beryl, for taking the time to answer them. I think we're ready to move on to our next speaker. If there's no other questions to be answered, again, we have the Q&A session afterwards. So if you didn't have a chance to ask your question now, we can do that later. With that, thank you, Beryl, again. Let's thank Beryl. And I'm excited to introduce our next speaker for today, Dr. Ciaran Seath. Ciaran is a postdoctoral scholar in the Macmillan Lab, and he started his work here just a little bit after I joined the lab. I think he was kind of just copying me, to be honest. And Ciaran is from Scotland, actually, and he did his undergrad and PhD work at the University of Strathclyde in Glasgow, which is not quite St. Andrews, but still a good institution. There he got his MChem in 2014, and then did his postdoctoral work at Strathclyde as well with Dr. Alan Watson. No relation to Dave there at all. And then working on, here he worked on chemoselective methods and transition metal catalysis. And then while a student at Strathclyde, he also spent some time at GSK in Pennsylvania, working on a range of hit-to-lead programs in medicinal chemistry. Which is where he first learned how much he really loved living and working in the USA. And so you fast forward to 2017, and Ciaran moved out to Emory University in Georgia to work with Professor Nate Dewey. Again, no relation to Dave there at all, where he worked on reductive photoredox catalysis. And after publishing a paper in Synlit, he was ready for his next venture. And being the curious and really sincere scientist that he is, he really sought to push his boundaries as a scientist and get out of his comfort zone and conduct research in a field that he had little to no experience with. And so he independently chose to do photoredox catalysis methodology in the Macmillan lab here at Princeton. But he actually did end up leaving his comfort zone and joining the growing chemical biology wing of Dave's lab, which is how we, or him and I, cross paths. And as I can talk more about in the Q&A session later on, working with postdocs is really a great experience. And Ciaran in particular has been a exceptionally kind, patient, and highly professional mentor with a very big heart and an even bigger liver. So it's been great to work with him in some ways, I guess. And I'm sure when he becomes an assistant big name professor at a prestigious R1 institution, after he finishes this postdoc in 5 years or so, he will be able to apply the mentorship skills he gained working with Beryl and I to his future grad students. But ultimately, he is an academic at heart. And as much as he loves to hear other people talk about him, there's nothing more that he loves than talking about himself. And so with that, I'd like to have you all join me in welcoming Ciaran to the virtual stage. Ciaran, you can now share your slides, not your CV, your slides. Thank you.
Thanks, James, for that interesting introduction. We actually have a tradition here at Princeton where the introducing person really roasts the presenter, and I was somewhat worried about what James would say about me, and you know, we certainly have a lot of experience together, and you know, maybe in the Q&A after the YouTube has ended, people can ask about some of James and I's experiences together over the last couple of years. But I'm really giving this talk because of James. He really offered this to me, and I thought that my experiences through to getting to Princeton are maybe slightly different to many of the other people, either in this seminar series, but also really like within this building. Like, as you can tell from James's introduction and also from my funny accent, I'm not American. I'm from Scotland, and this is broadly where I grew up in the north of Scotland. And you know, this is really the limit of civilization in the UK. Anything north of here, it's mostly just sheep. You know, it's about 400 miles to the nearest pharmaceutical company, like, which is round about here in England, and the nearest university is about 120 miles away in Aberdeen. This is Rosemarkie Beach. This is where I used to walk my dog every morning, and you can see from the kind of Google Maps image of where I went to high school. Fortress Academy is right next to the sea. You know, beautiful, warm, sunny sea that we always went swimming in, just like in Southern California, guys. And when I grew up, I was, you know, growing up in the country, you know, I really spent most of my time outside. I was an avid rugby player. You know, I loved adventuring out into the wilds and, you know, kayaking through rivers and doing a lot of mountain biking. You know, and in my teenage years, I think if you told me that, you know, 12 years from now, you're going to be working as a, you know, professional chemist, somewhat professional chemist, as James would say, at Princeton University, I would have said you were insane. That was certainly not something that I'd thought about at the time. You know, I don't know what I wanted to be, but, you know, chemist, and certainly a chemist at an institution like this was really not something on the cards. So the real question is, and what, you know, why I thought I would take James up on his offer to give this seminar to you all, was how did I end up at Princeton from this, you know, relatively isolated part of Scotland. And when you think about people at Princeton, you know, this is kind of the path, and not just Princeton, but many of these kind of top institutions. You think about, you know, they went to an undergrad at top 10 school like Berkeley or Yale, Beryl. And then they go on to graduate school with a famous professor like David Macmillan. And then if they want, they'll get their choice of jobs in big pharma, or they go on and to do a great postdoc, maybe with a Nobel laureate or someone like that. And then they go on and get a great academic position. And I think if you look around and look at the CVs of many big academics, this is broadly their path. But I think it's important to know that this is not the only path, and it's certainly not been mine. Mine's a little bit more like this, with about 100 different steps. And, you know, at some point, you know, I will end up with something my parents will consider a real job, fingers crossed. And it's important to say that your career path in chemistry is really not this linear path that, you know, perhaps Beryl has shown us shown us today. You know, and I think that's a good thing, that, you know, everyone in these big labs and everything has a slightly different outlook on life and chemistry, and I think that's a really great thing. I should, you know, I'm making fun of Beryl, obviously, for having this beautiful path with, you know, 4 JAX papers before she was 20. But, you know, in reality, it doesn't really matter how polished it looks on the outside. Everyone's journey through graduate school is, you know, is fraught with challenges, and it's always very difficult wherever you are. So really, where it all began for me was in my last year of high school. I had a really great chemistry teacher called Mrs. Sutherland, and what we did in our last year, she challenged everyone to do like a somewhat independent research projects. You know, she'd just give you a paper or whatever, and she says, "Oh, okay, go away and do this." And I picked up this project, this organic chemistry project, which was the synthesis of this antibacterial sulfanilamide from this starter material acetanilide. And this was, you know, a 3-step synthesis, which, you know, now with, you know, many years of experience, I'm really not concerned by. But at the time when I was 16, this was certainly a challenging prospect. And, you know, this proceeds pretty simply through electrophilic aromatic substitution with chlorosulfonic acid to form the sulfonyl chloride. This is quenched by ammonia, aqueous ammonia, to give the sulfonamide, and then hydrolysis with refluxing HCl takes off the acetyl group to give the final product. And I spent a huge amount of time trying to do this, and it took me about 7 attempts to get this, and including 2 trips to the ER. I eventually made it, and this was kind of where I started to really enjoy chemistry. You know, as a 16-year-old, a teenage boy, like you know, burning your hand with chlorosulfonic acid in the back of a classroom was I thought pretty cool. But, you know, something that I know now is, you know, chemical safety is very important. And it's something that I learned quite early, and I would urge you all to take this very seriously from the start of your career. It's just my some cautionary advice as a kind of senior statesman in a lab like this. So after this, you know, my teacher, Miss Sutherland, she says, "Oh, you should go and do chemistry. Like, you could, you know, you seem to enjoy this synthesis. You know, you can go and do this for a career." And I was like, "Okay, cool, let's do it." So I decided to do my undergraduate at the University of Strathclyde. This was kind of an interesting integrated master's program where you do a 3-year degree, followed by a year in industry, and then you come back and you do a master's. The university is located in Glasgow, so in the central belt of Scotland, which is by far the most populated part of the country. It's the 4th biggest city in the UK. It's very vibrant, has a really great nightlife, lots of things going on. And the university in general has a history of being very industry focused, so less academic and, you know, more practically inclined. You know, for many years it was a technical college, and, you know, gradually became a full university in the late 80s. It has about 20,000 students now, and about 2/3 of these are from the local area. And you know, one of the things that attracted me to the school was that the campus was in the center of a big city, and when you come from, you know, a village, you know, this was immediately enticing. So one of the great things that, you know, that I had at Strathclyde throughout my studies was I took the opportunity to travel as much as I could. And, you know, at the start of my 3rd year, I received a Tacit Scholarship, which is basically an exchange scholarship, and I went out to this very small college in Pennsylvania, or Pennsatucky, because it's kind of out in the sticks, called Franklin and Marshall College in Lancaster. This is, again, very different from Strathclyde in the middle of a city, where it's a PUI with, you know, 2,500 students. And here I kind of had my first experience with kind of independent research, or like academic research, with Professor Ryan Mell, who was a really great mentor, and he did some biochemistry looking at genetic code expansion and trying to use that to investigate protein function, which was really interesting, and prompted me I started to enjoy travel in the United States and some of the cool things that you can get to do out here, and also kind of gave me a kick up the ass and made me take my research a little bit more seriously when I went back to Strathclyde. And after about 6 months after I got back in the second semester of that year, I was applying for industry jobs for this year abroad. And I was very fortunate, and probably due to my time already in the US, I landed a job at GlaxoSmithKline in Upper Merion, just outside Philadelphia. GSK is a top 10 pharma company, and they have a huge consumer healthcare department and also a big pharmaceutical department. And I worked in the medicinal chemistry program there, and broadly worked on a couple different projects. These two molecules are, I guess, exemplar molecules. I didn't build these exact ones, but the first program I worked on was on the LPPLA2 inhibitors, and the daraplidib is the clinical compound that arose from this as a treatment for atherosclerosis. And this is a buildup of fat in the artery wall. And this kind of builds up over time, and when it gets big, it starts to, pieces fall off, and if they reach your heart or your brain, this leads to heart attack and stroke, and it's quite a deadly disease, and there's no current treatment for this. Ultimately, these compounds failed in clinical trials, but I certainly learned a lot in this project, and was starting to get excited by drug discovery. And the second half of my year, I worked on the second series of compounds, KI-696, which inhibits a protein-protein interaction between the proteins NRF2 and KEAP1. And these are broadly responsible for dealing with oxidative stress, so the effect of single oxygen in the cell. And this interaction was a proposed treatment for the disease, chronic obstructive pulmonary disease, which is basically where your lungs get damaged and they essentially stop working. And again, this is a very common disease in the West, in more aging population. But really, the most important part about this, again, this compound did not progress to the clinic, but for my learning, we had this incredible collaboration with Aztec Pharmaceuticals. And what was great about this is we, every time we made a molecule, a couple of weeks later, they gave us a crystal structure of this. And for me, learning about medicinal chemistry, this was really instructive. It's very easy to make a lot of molecules very quickly in this setting, but this helped us design them very effectively. So we could see how when we make a change to the molecule, you could see how it actually changes the shape of the molecule in the active site. And this got me very excited about pharmaceutical chemistry and how to build new interactions and how to gain potency and all these sorts of things. And also gave me a really good appreciation of what sorts of reactions are important for making these sorts of drug molecules. And broadly, across these two series, these two cross-coupling reactions really stood out as being very empowering. So in the NRF2 series, this Hayashi-Miura cross-coupling or conjugate addition, which is a reaction between, again, 1,4 conjugate acceptors and aryl boron species catalyzed by rhodium to make these. And these are very easy way to install stereocenters. And then the daraplidib example, doing the Suzuki-Miura cross-coupling, which again is a reaction with boronic acid, palladium, and an aryl bromide. And it's very facile with these methods to generate a lot of complexity very quickly and really scope out which compounds were going to be active and which ones weren't. So after this, this time at GSK, I came back, and at that time, I really wanted to continue this as my career going forward. And I ended up coming back to Strathclyde and working with a young professor, Dr. Alan Watson. And as James alluded to, Alan did his postdoc here at Princeton in David McMillan's group. And he had just started his research lab. He was in his second year at the time when I was in my master's. And I had a very small research group, and he still worked in the lab, and he's an incredibly enthusiastic character. And he was trying to pursue his research career between medicinal chemistry and transition metal catalysis. And this is, again, I said something that I was very interested about, after my time at GSK. So after I finished my master's in this group, which was somewhat successful, Alan asked me to stay for a PhD, and me and Alan get along very, very well. And his program was very themed towards things I wanted to do. So I was very happy to take him up on his offer, and I stayed on. And one of the big reasons for this was the group had this collaborative effort with GSK, the site in Stevenage in the south of England. And broadly, half of the lab worked on medicinal chemistry, looking at targets in fibrosis, cancer, and neurodegeneration. And then the other half of the lab worked on synthetic chemistry with catalysis, cross-coupling, and looking at the mechanism of these reactions. And these two sides of the lab kind of interwound with each other and fed into each other. So we would make molecules for the medicinal chemistry, and then, when challenges arose, we would try and come up with innovative solutions to these using modern catalytic pathways. And these three compounds at the bottom here are broadly what I, inspired the methods that I developed within my PhD. I'm only really going to focus on very quickly on this LPA1 antagonist from Amir Pharmaceuticals here. And the medicinal chemists in our group at the time were making this through a fairly clunky series of reactions. So what they would do is they would take this aryl boronic acid species, and this would couple to this aryl bromide, and then they would take this aryl chloride, which is unreactive in the first coupling, and turn it into a second boron species. And then this boron species would then go on and react with another aryl bromide to make this kind of triaryl motif, in 3 steps. And the nature of these reactions required them all to have purification. The boron species in the middle is also not the best on the column. And what we thought about was maybe we could come up with some methodologies that might enable us to make these compounds much faster. Ideally, we would have a method where we can mix and match all of these 3 aryl rings with different substitution patterns, and then run these in a high throughput manner to streamline the synthesis. When you only have a small lab of like 2 or 3 people, it's very important to optimize your time and get as many compounds out as you can, so you can really interrogate biology in a meaningful way. And for the undergraduates in this audience, you may know this, that at the time, just a few years before this, the Suzuki reaction had won the Nobel Prize. And this is, again, a really key reaction for the pharmaceutical industry, and it's one of the few transition metal catalyzed methods which is actually done on a ton scale in 3 different pharmaceuticals. And what we look to do is maybe add some value to this reaction. And the way we approached this was we took 2 different boron species, one that is protected by a pinnacle group, and one is protected by this group called amida. And then with 2 different aryl halides, a bromide, which is more reactive, and a chloride, which is less reactive, we were able to couple the 2 more reactive partners, the 2 in blue, and then in the same time, or slightly after balancing the rates, couple these 2 slowly reactive partners. And in this way, we were able to make these triaryl motifs in a very robust manner in 1 chemical step. And in this sense, we could set up these large screens, these large panels of reactions, and make hundreds of these compounds, in a single day. And then we ship them down to GSK, who do some biology, and then we can very quickly generate SAR. And shortly after this, I finished this study at the end of my first year, which is very fortunate for me, because what this enabled me to do was to start to apply for grants and funding to start go and travel places. I'd already got a bug for like traveling and seeing new labs and broadly coming to America. And that's why I titled my talk There and Back Again, because it seems to be all I do is fly across the Atlantic. And I went to work for Tom Snadden, who is, again, a young professor, Scottish professor, there's a theme here, at Indiana University. And one of the reasons, apart from being a friend of a friend, I worked for him is because his group was working on total synthesis and asymmetric catalysis. And whereas in my PhD, we were focused on transition metal catalysis and medicinal chemistry, so very much the more applied side of research, he was really looking at the more academic sides of the total synthesis, as Beryl mentioned, and also asymmetric catalysis, which is, again, broadly a more academic endeavor. And during my time there, I worked on this alkaloid morphine. This may be familiar to some of you. And I got about halfway through the synthesis, and this was really an incredible time for me. I learned a huge amount, not just about different group cultures and how to do synthesis. It really tightened up my experimental technique. When you're doing natural product synthesis, you have to be very exact in your technique, and everything has to be very, very rigorous. And broadly, this was an all-expensive paid trip to the US for 3 months, which was also a really nice break in the middle of my PhD. And when I got back, I finished another project, I guess, 6 to 8 months after I got back. And this, again, once you have these projects under your belt, you can apply for a lot of funding, travel grants and such. And I did as much as that as I could. 2 examples here. On the left, I went to this conference, which was up in the Lake District in England, which is a very beautiful part of England, very remote. And in these conferences, it was about a week. And all the academics and students and postdocs really all mingled together. And there's the picture that someone took for me of me talking to Professor Negishi, Nobel Prize winner, from a few slides ago, with also Professor Schoenebeck and Professor Morida. And again, I got the exposure to these academics, and I took along a lot of their advice. You know, they were very generous with their time, speaking to the students there, and that was really impactful for me, having to get to talk to these people that are much further along in their career in terms of Professor Negishi, and also slightly younger academics. And shortly after this, I attended the ACS in San Francisco with my boss Alan, and he introduced me to a bunch of his pals from Princeton, essentially. And a couple of them came to some of my talks, and ultimately offered me a postdoctoral position off the back of that. And one of the reasons I accepted to work with this guy called Nate Dewey is because he was, again, very enthusiastic about chemistry, which is something that I really look for in a boss, in an advisor. But he's also looking at a slightly different brand of chemistry. Throughout my PhD, the kind of rise of photoredox had been really occurring very strongly, driven by people here at Princeton and also other groups across the US. And what Nate in particular was looking to do was to use, instead of doing organometallic to electron chemistry with transition metals, he was looking to achieve pharmaceutically relevant bond formations with radicals. And his arguments for this: one, you don't have to use metals, which is better for the environment, but also the metals impose a number of restrictions on your chemistry in terms of what functional groups can be tolerated. And he's like, these radicals, if you control them, you can do anything. And I was like, this is great. I want to work for this guy. He's again so excited to have me in his group and to do some really cool research. So I moved to Atlanta. I don't know how, 3 years ago now, and joined Nate's group. It was about 6 or 7 people when I joined, and rose to about 14 by the time I left. He was pre-tenure at the time. He wasn't really in the lab when I was there, but probably the previous year he was. And one of the great things about working for pre-tenure professors, I found, like Nate would be my third, is that all their ideas are very fresh and they're very enthusiastic, and they really have a lot more time to deliver their knowledge and their experience to you, rather than the kind of environment that we have here at Princeton. And what inspired a lot of the work in Nate's lab was this reaction called the Birch reduction. And this is a very famous old reaction where you take an arene with sodium metal in liquid ammonia at cryogenic temperatures. And sodium is a very strong reductant. It wants to give up an electron. It has this reduction potential of minus 2.71 volts. You know, it really wants to be sodium plus and not sodium metal. And so it'll give an electron to these arenes to form these aryl radical anions. And upon further reduction and protonation gives these dearomatized products. So the strength of, you know, sodium's reducing power is enough to overcome the loss of aromaticity in these reduction steps. And while this is a really powerful and empowering reaction for organic chemists, it's kind of a nightmare to set up. And the difficulty and the lack of chemoselectivity in this reaction really limits its use in any real world setting. So we thought, well, is there another way that we could perhaps achieve these sorts of reactions to make these key intermediates, these aryl radical anions, under, you know, conditions that people might actually want to use? And we thought about using photocatalytic reduction. So in this sense, that the energy is donated by the blue light rather than inherent energy of sodium metal. And what we found was we could use these both organic catalysts, in this case, PTH, and phenothiazine, and also iridium PPY, this iridium complex. We could emulate the reducing power of sodium metal. So in this is kind of just a pathway along these, you have the organic molecules and their reduction potentials at the top, and then the catalysts or sodium metal at the bottom. So these two catalysts sit around here, and sodium metal is kind of up here around 3. So we're not quite there. And you know, there's certainly ways to kind of increase this in the literature more recently, but at the time, you know, this was kind of the limit of what you could do. We started to use these really strongly reducing excited states to start to do some new chemistry. And like I mentioned previously, Nate is really interested and really driven by making functional groups that are very prevalent in the pharmaceutical and agrochemical industries. And you know, a lot of these functional groups, such as a difluoromethyl group or a phenethylamine, phenethyl alcohol, or an alkyl difluoro group, these can be stumbling blocks for synthetic chemists in the industry. And you know, if you perhaps have one of these, this can add a number of steps into your syntheses and really limit the amount of molecules you can make in a really dynamic manner. And we challenged these problems and came up with some solutions. And again, you can have a look at the papers that we published at the bottom of the slide here. And just to take you through one of these examples, this fluoropyram, this agrochemical, we decided to break this apart at this bond here. And this can be reduced back to the aryl the bromopyridine star material, and also this enamide star material. And if you treat this mixture with a strongly reducing catalyst and dump an electron into this bromopyridine, it's going to form a pyridine radical anion, which is a transient intermediate, which very rapidly spits out bromide to give you a neutral pyridine radical back. This pyridine radical can then engage an alkene in alkene addition, and this will give you this intermediate here with this alpha amido radical. This radical can then be quenched by hydrogen atom transfer catalyst, such as a thiol, to give you this final molecule in a really efficient route. And what we liked about this was we were able to change both this left-hand side, this alkene, and this pyridine unit in a very modular way and make a number of these analogs of this very important agrochemical in very short yield, very short step count. And this was previously a 7-step synthesis by the agrochemical company, and we were able to achieve it in 2 in very high yield. And this is something that we really aim to do with a lot of our methods, was to make these very difficult and quite challenging motifs in a very short period of time, so to really enable medicinal chemists and agrochemical practitioners. And after almost a couple of years in his lab, I was thinking about my future career, and Nate said, look, before you go look for an academic job or an industrial job, go to Princeton, go and work in a big lab with all the best people in the world. I think this will be really important for your development before you, enter an actual job. And I was like, okay, let's do it. And he basically phoned up Dave, who I had met at a conference earlier that year, and said, hey, look, I've got this guy. I think he'll make a good addition to your lab. And Dave's like, sure, whatever. You know, this is how all these things go on behind closed doors. You think it's a legitimate process, and it's typically not. So in May 2019, I arrived in Princeton, broadly terrified. And as I've shown you, I worked in a number of labs which are very small. You know, maybe maximum about 14 people, and you know, maybe one postdoc. And in Emory, I was the only postdoc in the group, and I was confronted with the Macmillan lab, which is 20 postdocs and 20 graduate students. You know, and they're all from Berkeley, and they're very large, and everyone's extremely talented. And I immediately felt kind of overwhelmed and had a huge dose of imposter syndrome. I felt like I wasn't really good enough to be in the lab, and you know, I didn't really know anything compared to anyone else. And you know, this is, I think, a very common thing for people, especially coming into these sorts of environments when everyone around you is so talented. And I think, you know, over the years, this has faded a little bit with me, but I think it's important to highlight that even after however many years, 3 different research groups and time at a global pharmaceutical company, I was still terrified when I joined this group, and remained so for a good few months before I really found my feet here. One of the things which really drove that in was when I joined, I wasn't really looking to do organic methodology anymore. I really wanted to do something completely different. And I knew that the lab was working on, it just started by James and one of his co-workers, this new field where we're doing photochemistry, but inside the cell. And you've heard Beryl talk today about the challenges that are associated with moving from small molecules just to proteins. You know, this was another step along that pathway where we're dealing with whole cells, and we're growing, culturing cancer cells and all these things. And I basically, as an organic chemist, I needed to completely retrain. I needed to learn everything all over again. And this was, yeah, again, certainly a terrifying prospect, you know, in my later years. And, you know, this is kind of the situation in most labs. You know, there's James here as the PhD student playing with a pipette, and there's, you know, a postdoc, some sensible postdoc trying to save the day. And when I came into the Macmillan lab, I really felt like I was back in the high chair, relearning everything. And Dave's got his back turned and ignoring us all. And certainly after 2 years, I would say that I now feel like the postdoc again, and feel certainly a lot more comfortable in my time. And I think that's just the benefit of experience, and it's something you'll also find that the skills that you have now are very translatable. As a scientist, when you get your PhD, whether you're doing your continuing research in the same field or not, you've learned how to solve problems, and that was something that occurred to me over my time here. And now, after 2 years, I'm now leading 4 different collaborations, you know, across the US with some really fantastic physicians and chemical biologists, and, you know, very comfortable talking about science with really some of the smartest people across the country. And, you know, just before I finish, I want to point out that really across many years now doing this, I've had the privilege to work with and become very good friends with some really incredible people. And when you're struggling through a PhD and that the times aren't great, you know, the people around you really lift you up. So I've shown some people here. This is some of my friends in the Watson group. This was at ACS San Diego last year. So many years after I finished in that group, and we all met up and you know, saw Alan's kids and had a great time. You know, sometimes with the Dewey group. In Nate's house, and also in the Macmillan group, we went to Colorado. You can see James on the end here, and also yeah, Beryl here next to a very startled Dave. So yeah, I just want to, you know, the people you meet along your journey here are going to be your friends for life, and I think that's a really important lesson to really cherish these people as you go through your career. Ooh, back. So yeah, again, Beryl also did something similar, some words of wisdom, I guess, for my advice after many years in this, doing this is, it doesn't really matter where you start, whether it's in a village in the north of Scotland or, a private high school like Beryl. If you work hard and you're ambitious, then you're going to get to where you want to go. And the American system is quite democratized, and if you're successful, people are really happy to really support you. And that leads me on to networking. Everywhere I've gone, it's been from networking, and pulling on connections that you didn't know you had. People are very happy to help you. And I think what you don't realize from the outside is that this is really how a lot of things are done. And it's okay to feel like you're out of your depth. I was absolutely terrified when I came here. But after a couple of years, I'm very confident doing the stuff I'm doing. And I think this is the most exciting research I've ever done in my life. Take opportunities, take the advantage to do as much cool stuff as you can. Don't think, oh, well, I don't want to go because, I have to do work or whatever. Like, just do it, and you'll be better off for it. And then have as much fun as you can, because this is a very interesting time where your life is very, it doesn't have a huge amount of structure, and you can, really take a lot of time to do some fun things with some really interesting people like James. So just some acknowledgements to kick off, to finish the talk. I'd like to thank Dave. This is the chemical biology team here at Princeton, and we've all gone from being that little undergrad in the high chair, not knowing anything about working with cells and biology, to being a pretty high functioning unit, I think. Again, big thanks to Barb and Anthony, or my collaborators in Tom Muir's lab. And then Alan and Glenn, my advisors in my PhD, and then Nate Dewey and the Dewey group for hosting me at Emory, for having a great time there as well. And thank you all for listening, and I'll be happy to take any questions.
All right, well, let's all give Ciaran a big round of virtual applause. All right, well, thank you, Ciaran. That was great. That was a lot of fun, and really good points there, of course. You guys want to remember to have fun in grad school and as you go throughout your academic career. So really enjoyable to see that. All right, so with that, I'm sure you all have lots of questions for Ciaran. He has shared a lot of his life and has had a long journey to this point. So lots of advice to give. So definitely capitalize on that. So again, you can ask your questions in the chat or raise your hand and I'll call on you. Yeah, go for it. All right, Madison, go ahead and you can ask your question.
Yeah, so you mentioned, I just basically wanted to know the difference between like medical chemistry and synthetic chemistry. I know it's like kind of two different routes that are intertwined in different ways, but what influenced your choice to go in one or the other, and what advice do you have to people who are also considering, one of those fields?
Yeah, that's a good question. I would say that medicinal chemistry, the molecules you're synthesizing are important for their function. And in a more synthetic sense, the molecules you're synthesizing are challenging or require elegant syntheses, and it's more about the beauty of chemistry, so to speak, and it's less about what the molecule actually does at the end. And broadly, they give slightly different types of training. So pure total synthesis type chemistry, you really become an excellent organic chemist with your knowledge of literature and how to perform reactions. Whereas if you go down a more medicinal chemistry route, you don't necessarily gain the same level of practical talent, but you also learn a lot more about other aspects of how to do medicinal chemistry. There's a lot more to it than just making molecules. It's making the right molecules, and that's a different skill entirely. But it depends what you want your career to be, really. And they're both good, both fun.
Thank you.
Great. Any more questions? Okay, so we have a question from a YouTube viewer. The viewer asked, I'm a second-year chemistry major. What's the difference between a PhD and a postdoc? And why do you do a postdoc?
So the difference is that you have a PhD broadly. So a lot of people, I would say, do a postdoc. When you finish your PhD, you need to choose a job, right? You need to choose a career path. And if you want to be a medicinal chemist, some medicinal chemistry companies or groups, they want you to have done a postdoc just to be more experienced. Not all companies require this, and they won't require it from every candidate either. It really depends on how successful you've been as a PhD student, what advisor you work for. Some companies are, I would say, quite snobbish, and that they want you to have worked with someone famous that they know, and you know that often requires you to do a postdoc. If you want to be an academic, like I do, it's absolutely required. You need to go away and do something different and prove that you can be successful in more than one environment. So yeah, it's staff. Technically, you're a member of staff at the university, but just doing full-time research. So you don't have to do any classes or exams or write a thesis or anything like that. It's pure research.
Great. So we have another question from YouTube. The viewer asked, mitochemistry is Burke, right? Did you purchase the mito compounds yourself, or did you make the compounds yourself, or did you purchase them?
Yeah, it is indeed. That is, the mitas are developed by Marty Burke's group, where we made everything. There's a great difference between my grad school experience and perhaps James's grad school experience, where I had to make all my start materials, and James doesn't make anything; he just buys it. But it's by virtue of the wealth of the lab. Beryl talked about them at my own lab being very wealthy, and we are, and that saves people a lot of time in that sense, so they can do the really important experiments, and not spend their time making boron compounds like I did.
Right, Emily, I saw you had raised your hand.
Hello, I really enjoyed your talk. It was really interesting to see how you went from industry and then on to grad school. My question is, what was it like transitioning from doing organic chemistry research to chemical biology research?
Yeah, that's a good question. Scary, really scary. Yeah, I think the first little time was like, it was pretty tough, but there was a couple of us doing it, so we were all learning together. There's at the start there was 3 postdocs and James, me, 2 other postdocs, and I would say this group of people is one of the most incredible group that I've ever worked with. So we supported each other a lot, and honestly, we really didn't, like, looking back now, we really didn't know anything for a long time, but it was okay because Dave didn't know anything either. So you just got to be one step ahead of your boss. But you know, after about a year, I think we really knew what we were doing. And that, you know, that it is scary, but that's a good thing. It's a good thing. I think we're all, as scientists, we want to like learn new stuff and do new stuff, and that was what motivated me to do it.
Thank you so much.
Great.
That's really interesting.
Yeah, lots of bootstrapping on our end. And so Jennifer asked, how different was your experience in grad school and in industry?
Wildly different. So industry, I had a really great time when I was at GSK. Really great time. I enjoyed it a lot. But it's a work atmosphere. You are working at a company. It's not, if you don't make the compound that day, you go home, you have a great evening at 4 o'clock, and you hang out with your friends, and then you come in the next day and you try again. And in grad school, especially, so my PhD was only 3 years. I was funded by, I had a charity fellowship, and it's quite short time. And if you need to produce an amount of research in that time, there's a pressure. There's also pressure from your supervisor, which is less prevalent in industry. They're aware that their employees have a life outside of the lab. So yeah, it's very different. I really enjoyed grad school, and I enjoyed my time in industry, but I didn't work Saturdays in industry. I didn't work Sundays in industry. So yeah, it's very wildly different. but one, they all encouraged me. Everyone there, because I said when I finished my time at GSK, I was like, I'd love to come back. I had a great time. And they're like, right, go do a PhD. Go do a really hard PhD for a few years and then come back when you know things.
Right. Thanks again, Ciaran. Any more questions? Any questions? Again, we have the Q&A session right after this. But if anyone wants to get any more questions in before that. All right, so I think that about closes the live session, at least. So I'm going to hand it off to whoever is in charge of closing that down before we start our Q&A.
Yeah, thank you everyone so much for joining us. I would like to have everyone join me in giving a round of applause for our speakers, Beryl and Ciaran, as well as James for being an incredible moderator. And with that, that closes out the live portion of this.